Welcome back to Applied AI Engineer. So far Atlas has been a single agent, one reasoning loop, calling one tool at a time. Today we go a level up. We orchestrate several agents inside an explicit graph. We'll build a planner that breaks a goal into steps, workers that each carry out one step, and a supervisor that reviews progress and decides what happens next. We'll add a human-in-the-loop checkpoint, and just as important, we'll be honest about when multi-agent actually helps and when it just burns latency and money. By the end you'll have a real graph executing across nodes, with each node's reasoning driven by a genuine model call. Quick recap. In episode 10 we gave Atlas a kit of real tools, a retriever, a calculator, a database, and let a single agent choose between them in a loop. That single agent design is the right default, and most apps should stop there. But some jobs are easier when you split them across agents that each own a clear job. That's orchestration, and LangGraph is how we declare it, typed state, named nodes, and edges that route control between them. On the left is what we already have, one agent, one loop, one context window holding everything. On the right is the multi-agent shape. A planner decides what needs doing, and separate workers each handle a piece with their own clean context. Splitting roles can make each agent simpler and more reliable. But notice every box on the right is another model call. Coordination is never free. We'll return to that trade-off with hard numbers later. First, let's understand the patterns. There are a handful of orchestration patterns you'll see again and again. The two most useful are planner worker and supervisor. Let's define them precisely, because the names get thrown around loosely, and then we'll build them for real. 5 terms. A planner takes the user's goal and decomposes it into ordered subtasks. A worker executes exactly one of those subtasks at a time. A supervisor is the router. It looks at the current state and decides which agent runs next or whether the job is done. A subagent is just a worker scoped to one narrow skill. And the graph is the whole thing, the nodes, and the edges that move control between them. Hold those, and the code reads itself. Why not just a chain? A chain is a straight line, step A, then B, then C, with no decisions. But real work branches and loops, do a task, check progress, maybe redo it, maybe move on. A graph captures that. The key feature LangGraph adds over a plain chain is the conditional edge, a small Python function that inspects the shared state and picks the next node. The agents do the thinking inside nodes. That routing function is plain, deterministic code. That split is the heart of today's episode. Before we wire the graph, we need each node to actually reason with a model. This dev box has no API key, but the Claude Code CLI is authenticated, so we'll drive each node's reasoning through a one-function adapter over that CLI. In production you'd swap the body for the Anthropic SDK, and the node code wouldn't change. Here's the whole adapter. The ask function takes a prompt and an optional system instruction and returns plain text. The details that matter on this machine, we feed the prompt on standard input so multiline prompts survive, and we hand the CLI a fresh, throwaway config directory holding only the auth credentials, so each call is a clean turn that answers exactly what we asked. The crucial point is the shape. Every node will call ask, and ask hides the provider entirely, exactly like the chat adapter we built in episode 1. Every LangGraph app starts with a state schema, the shared blackboard every node reads from and writes to. Ours is a plain typed dict. The goal and plan are obvious. The cursor tracks which subtask is next. And look closely at done and notes. That annotated wrapper with operator.add is a reducer. It tells LangGraph that when a node returns a value for these fields, append it to the list rather than replace it. That's how each worker pass accumulates results instead of clobbering the last one. Here's the planner node. It's a function that takes the state and returns a dict of updates. It asks the model to break the goal into 3 short subtasks, 1 per line. Then, and this is the recurring theme Python takes over, we split the reply into lines, strip any stray bullet characters, and keep the first 3. The model does the creative decomposition. Our code turns its words into a clean, structured list the rest of the graph can rely on. It writes the plan back to state and resets the cursor to 0. The worker is deliberately narrow. It executes exactly one subtask, the one under the cursor, and nothing more. It returns 3 things: the task label it finished, its one-sentence result, and the cursor advanced by 1. Because done and notes use the append reducer, each visit adds to those lists. This single responsibility design is what makes the loop clean. The worker never has to know how many tasks exist or what comes next. That decision belongs to the supervisor. The supervisor node reviews progress and logs it. In a richer app it might replan or grade the work, but here it simply marks the checkpoint. The real decision lives in route, the conditionalage function. It compares the cursor to the plan length and returns either the string worker to loop back for the next task or end to stop. This is worth pausing on. The routing logic, the brain of the supervisor pattern, is ordinary, testable Python. We don't ask a model to decide control flow when a simple rule will do. Now we assemble it. We register the 3 nodes, then declare the edges. Start flows into the planner into the worker into the supervisor. The last line is the important one, a conditional edge from the supervisor, governed by our route function, that can go either back to the worker or to end. That single conditional edge is what turns a straight chain into a loop. The worker runs once per task until the supervisor says stop. Compile, and we have a runnable graph. Here's the whole graph in one picture. Control enters at start and hits the planner, which fills in the subtasks. Then it's a cycle. Worker does one task, supervisor reviews, and the conditional edge either loops back to the worker for the next task or exits to end. The orange edge is the loop. Remember the division of labor. The blue, green, and purple nodes reason with the model. The gray edges are deterministic Python. Let's run it and watch control actually move. This is a genuine run. The goal was to plan a 30-minute talk on vector databases. Watch the trace. The planner emits 3 subtasks. Then the cycle turns. Worker 0 defines the turn. Supervisor logs 1 of 3 done. Worker 1 explains the concepts. Supervisor logs 2 of 3. Worker 2 outlines the timing, and the supervisor sees nothing remaining. Control genuinely moved planner, worker, supervisor, worker, supervisor, worker, supervisor, and then the conditional edge routed to end. That's orchestration you can read line by line. And here's the payoff of that append reducer. The final state holds all 3 tasks paired with all 3 results. The whole job, assembled from independent worker passes, not just the last step's output. Each worker had a clean, narrow context. The graph stitched their outputs together. This is the shape of a planner worker supervisor system. Decompose, execute piece by piece, accumulate, and stop when the plan is exhausted. A multi-agent system takes actions on its own. For anything risky, sending an email, spending money, deleting data, you want a human checkpoint before it acts. LangGraph has a first-class primitive for exactly this, and it's surprisingly clean. The idea is a deliberate pause. A node calls interrupt with some payload, say, a draft about to be sent. The graph stops right there and surfaces that payload to your application. Because a checkpointer has saved the entire state, nothing is lost while it waits, even for hours. Your app shows the payload to a reviewer, collects an approve or reject decision, and then resumes the graph with that decision. This is how you put a human gate in front of an autonomous system without rewriting it. Here's the smallest meaningful version. The gate node calls interrupt with the draft to review, and execution stops at that line. The one thing that makes this work is the checkpointer we pass at compile time. Without it, there would be no saved state to resume from. We use the in-memory saver here, but in production this is a database, so a graph can pause on one request and resume on a completely different one, even days later. That single argument is the difference between a toy and a durable workflow. Running it has two phases. The first invoke runs until the interrupt, then returns, and the post result carries the payload we passed in under the interrupt key. Our app reads that, shows it to a human, and gets a verdict. Then we invoke a second time, but instead of new input we pass a command with resume equals approve. The thread ID in the config ties this resume to the exact post run. The gate node picks up right where interrupt left off, as if the function had simply returned that decision. And there it is, end to end. The first line is the graph pausing and handing our application the draft to review. The second line is the graph resuming after the human approved, with sent now true. Between those two lines, real time passed and a real decision was made. The graph just waited, holding its state. Swap approve for reject and sent comes back false, and the action never happens. That's a production approval gate in about a dozen lines. Now the candid part, because it's the most valuable thing in this episode. Multi-agent architectures are fashionable, and they are often the wrong choice. Let's be clear-eyed about the costs before you reach for one. Here's the honest scorecard. Multi-agent helps when agents have genuinely distinct skills or tool sets, when a job is too long to fit one context, when subtasks can run in parallel, or when you want an explicit review gate. It hurts in ways that are easy to underestimate. Every handoff is another model call, so latency and cost multiply, context gets dropped between agents that don't share memory, and you've added moving parts that are harder to debug. The uncomfortable truth is that a single, well-equipped agent solves most problems you'd be tempted to throw a committee at. Let's make the cost concrete. Our little graph made one planner call plus 3 worker calls, 4 model round trips, and because each worker depends on the cursor from the last, they ran one after another. The user waits for the sum of those latencies, and you pay for the sum of those tokens. A single agent with the same tools might have answered in 1 or 2 calls. Multi-agent buys you structure and clean contexts, but you pay for it in time and money on every single run. So here's the rule I'd give a teammate. Start with one agent and a solid tool set, the episode 10 design. Only reach for a graph when that single agent visibly strains, when contexts overflow, or when the work has a clean seam between distinct skills. Keep your routing in deterministic Python wherever a rule will do, instead of paying a model to decide control flow. Put a human gate in front of anything irreversible. And actually measure latency and cost before and after, because the elegant diagram is not the same as a faster, cheaper product. One quick note on the wider landscape, so you are not locked into one library's vocabulary. OpenAI's Agents SDK models this as handoffs between agents. CrewAI and AutoGen frame it as row-based agents or group chats. Under the names, they share the same skeleton we built: shared state, agents as nodes, and a routing decision between them. LangGraph's contribution is making the state and the edges explicit and inspectable. Learn the pattern, decompose, execute, route, gate, and any of these frameworks becomes a detail you can pick up in an afternoon. Step back and look at what you now have. A genuine planner worker supervisor graph with typed state and append reducers so results accumulate. A conditional edge that turns a chain into a loop, running the worker once per task. A human-in-the-loop gate that pauses an autonomous run for approval and resumes cleanly. And most important, the judgment to know when one agent would have been simpler, faster, and cheaper. That last skill is what separates an engineer from an architecture astronaut. Let's recap. Orchestration is just three things: shared state, agents as nodes, and edges that route control. A planner decomposes the goal, workers execute one step each, and a supervisor decides what runs next, with the routing kept in plain Python. You can pause the whole thing for a human and resume it later thanks to interrupt and a checkpointer. And you'll spend that power carefully, because every hop costs latency and money. Notice we leaned on the checkpointer to make the graph durable, and that idea of remembering state is exactly where we go next. Episode 12 is Memory and State, giving Atlas a real memory so it carries context across turns and sessions. See you there.